I am Amin Abedini, a master's student at the University of Toronto in Transportation Research Institute. I did my master under the supervision of Professor Eric Miller, and today I'm going to present my master thesis. I have developed a machine learning framework for the clustering and calibration of roadway performance model that can be applied in the large-scale traffic assignment. Here is the overview of today's presentation. First, we will go through the background and the motivation of the research work that I have done. Then we will see the research questions that I'm going to answer them till the end of this presentation. Then we will go a little bit through the literature review, and we will see where is the study area and the data sources that I have used for the calibration of roadway performance models. And then we will see the framework structure and specifications, and then we will see the results that is generated by that framework. The conclusion and future works are the next section, and at the end we have the references. And at the end of this presentation, we have about 10 minutes for your questions. If you have any question, you can ask at the end of the presentation. Okay. Let's imagine yourself, you are driving in Highway 401 and you are stuck in a traffic, and you are just looking at your mobile phone and you want to see how many hours or minutes you have to drive to reach your destination. Well, this is where my research can contribute to your feeling at that moment and may lower your anger. I was talking about traffic congestion. Traffic congestion is a severe problem in our cities. And we, as transportation engineers, want to mitigate this problem. In order to do that, we have to use an evidence-based tool. We call it travel demand models in our works. Travel demand models contains two parts. One part is the travel demand, the other part is the transportation supply. Both parts should be calibrated by the real-world data. The travel demand side has been under calibration during the past years, but the supply side was not calibrated with the empirical data during the past years. Therefore, one of the motivation of the research work, of my research work, is to calibrate the supply side of the transportation for the travel demand models by the imaging data sources. Here are the research questions that I'm going to answer till the end of this presentation. First, we want to evaluate the performance of the GTHA road network and see any temporal or spatial pattern through the network. And also, I'm going to examine different machine learning methods for clustering traffic-related data. And afterwards, we will see and understand the impact of roadway physical attributes on the roadway performance. For example, the land use close to the roadway and the number of lanes and speed limits. And we want to see how these attributes can influence the roadway performance. And at the end, we will see the effects of the long-term planned and unexpected short-term incidents on the performance of the roadway, for example, weather condition or accidents. Let's go a little bit through the literature. Here is the travel demand model, which is used by the regional municipalities in Greater Toronto Hamilton area. We call it GTHA model. In the first stages of this model, the demand is generated, the travel demand. And at the last stage, we have the network assignment or traffic assignment. And in this model, the interaction between transportation supply and traffic and travel demand is seen. Here, in the traffic assignment, we have two submodels, which the names are route choice submodel and network loading submodel. In the network loading submodel, we have path flows and infrastructure supply as inputs, and this submodel will generate the travel demands. And the travel demands will be another input besides the travel demand to the route choice submodel. And this loop will continue until it converges to the user equilibrium. From the infrastructure supply side, we have a volume delay function, which is the main purpose of my study. And I'm going to get more details about this in the next slides. Volume delay function is non-linear mathematical formulation that connects two key traffic factors, the traffic volume and the travel time. And this model is built based on the simplified macroscopic behavior of the vehicles. Here we have a typical volume delay function. On the x-axis, we have the saturation rate, which is calculated by the volume over the capacity of the roadway. And on the y-axis, we have the delay factor, which is calculated by dividing the speed by the free flow speed. And this diagram has two regimes. One of them is uncongested regime, the other one is congested regime. It starts from the free flow speed in this stage, and it rises mildly until it reaches to the capacity value. And afterwards, it has a steep increase and it will go up and up. And as you can see, this diagram is monotonically increasing, and we can say that more traffic volume can result in more travel time. Volume delay function is used as the objective function in the travel time minimization problem, which is used in traffic assignment. There are various formulations proposed for volume delay function since 1950. Some of them have a theoretical background, and some others have empirical background. The most common used volume delay function is BPR function, which is used both in industry and literature. Here we have the tangent function. In 1992, a group at University of Toronto implemented and tested various volume delay function within any traffic assignment, and they concluded that the tangent function is the best function to be used for the region because of its speed of convergence and also its simplistic functional form. And then in 1996, Michael Mahood see the effects of signalized intersection and streetcars on the performance of the roadway. This function follows a BPR function in uncongested regime, and afterwards, when it passes the capacity value, it just follows a simplified deterministic queuing theory. The study area of my research study is Greater Toronto Hamilton area. This area contains 6 municipalities, and it contains 20% of Canada's population. And the population of this region has grown by 5% during the last 5 years. And the population density in this region is about 883 persons per square kilometer. And this region is one of the largest metropolitan areas in North America. The main data source that I have used for my research is a street light. A street light is an on-demand mobility analytics platform that they process the GPS traces of the mobile phones, and they generate some transportation-related metrics, for example, origin-destination metrics, or historical route choice behavior between origin and destination, the turning movement and signalized intersection, and also the segment analysis feature. I only use the segment analysis feature for my research work, and I got the 15 minutes aggregated traffic count and average speed from their platform. I selected 2019 as the year of study because I want a year that is not disrupted by COVID-19 pandemic. The other data source that I have used is GTHA model version 4 outputs. GTHA model is an integrated activity-based travel demand model which is used by regional municipalities in Greater Toronto Hamilton area. And it contains all 24-hour travel patterns, but the main focus of this study is only the morning rush hour, which is from 6 a.m. to 9 a.m. The other data source that I have used is GTHA road network, which is based on the GTHA model network. We have 28,000 kilometers of the roadway, from which 10% are highway, and we have about 50,000 road segments within the network. The other data source that I use is Network Coding Standard 2016. The calibrated values are compared to the existing values in this standard that I am going to show you in the results section. And in this network coding standard, we have the information regarding the attributes of elements in the GTHA model network. And this coding standard is updated every 5 years. And it contains road functional classes and also the speed range and lane capacity for road segments in the network. The last data source that I have used is DMTI land use data, which is at the dissemination scale. It contains about 7 categories: residential, commercial, institutional, industrial, parks, open area, and water. And I use the latest version of this land use data, which is for 2016. Here is the framework that I have proposed for cleaning, classifying, and calibrating the traffic flow fundamental diagram. This framework contains 3 stages, and in each stage we want to detect something. For example, in the first stage we want to detect typical days. In the second stage we want to detect normal traffic condition, and in the third stage we want to detect road functional classes. I will go through this framework in details in next slides. Before going through the first stage of the clustering, we have to do some preliminary works. First, we have to get the data from a Streetlight. In order to sample the data points, we use one run of the GTHA model-based ME traffic assignment, and we selected the road segment that experienced more traffic congestion during the day. We use the criterion of volume over capacity greater than 0.9 for the selection of the roadway, and we selected about 791 road segments among the 3,600 road segments that has this criterion. And the other stage that we have done before the first stage of the clustering is data cleaning. There were some data points that are for the heavy trucks at night that have low travel speed. We eliminate these data points by using the threshold on the speed and density, and also we clean the database from the missing data. In the first stage of the clustering, we filter long-term planned incidents and we find the typical days. In order to do that, we implemented principal component analysis combined with Bayesian and Gaussian mixture clustering. And for each day, we have 96 15-minute in aggregated speed flow pairs, and we imported these features to the PCA. Here we have the table that the rows are the days of the year, and the colors are the speed and volume in different time of the day. Here is the visualization of the first stage of the clustering. On the left-hand side, we have the scores loading pipeline, which is for the first and second component of the PCA. The red arrows are the traffic flow and travel speed for different time of the day, and the black text are the days of the year. As you can see, there is a distinct pattern here. There's 2 distinct clusters here. I examined different central-based, distribution-based, connectivity-based, unsupervised machine learning method, and I concluded that the distribution-based method is performing better than other clustering method. Therefore, I use Bayesian and Gaussian mixture clustering for this purpose. And as you can see, there are 2 clusters here. One of them is typical days, which is normal weekdays, and the other one is unusual days, which is which are weekends, holidays, and also work zone places. Before getting to the second stage of the clustering, we have to engineer some features. The data that we have is based on the 15-minute interval. We should do a rolling window on this data to get the 1 hour data. And we average the speed and we sum the flows through each 1 hour rolling window. And also we applied the modified range model to calibrate the traffic flow fundamental diagram. This model is a two-regime model that has a straight line in the free flow speed condition, and afterward there is a convex shape in the congested regime. We have selected a speed density equation among the three fundamental equations that we have for the traffic flow. The selection is based on the fact that this equation has a one-to-one mapping, which is good for calibration of traffic flow. And the function that I showed you in the previous slide has 4 parameters that should be calibrated with the observed data. The first one is free flow speed, the second one is breaking point density, the third one is power term, and the last one is jam density. We considered the jam density to be 144, which we consider that based on the fact that the spacing between bumper to bumper of the vehicles are 7 meters. And when the vehicles are in the jam density, we can say that if there is 1,000 meters, if we divide this number by 7 meters, we will have this number, which will be the jam density of that road section. We use a nonlinear least square method for the optimization and also the SciPy library in Python. In the second stage of the clustering, we want to remove days with unusual traffic patterns. I mean the adverse weather condition and accidents. In order to do that, we implemented the modified hierarchical clustering. The similarity matrix in this clustering method are selected to be area between the curves. And we put the number of clusters to be 10, and we eliminate the cluster that have data points less than 30. As you can see, here we have the days that have typical days. This is the result of the first stage of the clustering after applying the calibration. After applying the hierarchical clustering, we will have about 168 typical days that has normal traffic condition, and we will calculate the mean value of the calibrated parameters for this one, and we will use that in this third stage of the clustering. In the third stage of the clustering, we want to find the road functional classes, and we import the mean calibrated parameters of all the road segments that we have in this stage. Also, we applied the modified hierarchical clustering as the second stage of the clustering that I said before. And we choose the number of clusters based on our own intuition. For example, here I have selected 7 as the number of clusters, but in the results section I will show you the diagram which I selected 4 as a number of clusters. Okay, let's go through the result of the study that I have done. Here is the free flow speed. On the right hand side we have the calibrated free flow speed, and in the left hand side we have the existing value in the network coding standard. It seems that the colors which is shown here is little bit different from what I can see in my laptop, but I can tell you the story behind the colors. In the downtown core, the colors are light yellow, but in the downtown borders, the colors are mostly darker yellow. It means that based on the observed data in the downtown core, we have a lower free flow speed compared to the road segments which are located on the downtown borders. The reason beside this might be the fact that the spacing between the signalized intersection in the downtown core are close to each other, and also the presence of the street car and also the pedestrian flow can have some influence on the performance of the traffic flow. And in the left-hand side, we have the values based on the NCS 16. As you can see here, the free flow speed is reported to be 40 to 50 based on the network coding standard, but we see wider variation of free flow speed in the downtown, which starts from 20 kilometers per hour in the downtown core, and it increases to 60 in the downtown borders. Also, we can see the same pattern for the capacity. As I said before, here in the downtown core, we see less capacity compared to the downtown borders. And the reason can be the same as the one that I said for the free flow speed. The capacity in the NCS 16 for the downtown region varies between 500 to 700, but the calibrated capacity based on the observed data tells us another story. It has more variation, which starts from 300 to 1,200. These capacity values are based on the vehicle per hour per lane, because some of the road segments have 2 lanes, some of the road segments have 3 lanes, and we have to normalize the capacity value based on the lane. I showed you the result of the downtown, and right now I'm going to show you the result of the whole network. Here are the total of 791 road segments in the network. Here in the right hand side we have the calibrated flow speed based on the observed data, and in the left hand side we have the values based on the network coding standard. As you can see, there is a same pattern through both of them, but calibrated free flow speed contains more variation, which start from 20 kilometers per hour in the downtown core, and it becomes more when we get far from the downtown. And as you can see here, we have the highways, which are colored as green. Also, we can have the same pattern for the capacity, which you can see here. Let's discuss about the free flow speed and capacity that we have seen in the previous slides. Here only we want to talk about free flow speed, and the diagram here is calculated based on the deduction of NCS 16 and calibrated observed data. The green color means that NCS 16 is overestimating the value, and the red color means that NCS 16 is underestimating the value. As you can see, most of the road segments in this area are colored as green. A little bit of them are red, as you can see here. It means that free flow speed is overestimated in NCS 16. This comparison curve also shows us this trend. We have NCS 16 values on the x-axis, and we have calibrated parameters, calibrated free flow speed on the y-axis. And here is the identity line, and we can compare the data points with the identity line. As the data points are below the identity line, we can say that the free flow speed is overestimated in NCS 16. Also, we have we can have same trend for the capacity. Here, as you can see, most road segments are colored light green, which means that most of them are well calibrated. But some road segments, especially the highways, are underestimated in NC16. This comparison curve also give us the same insight. If we exclude the highways, these two lines, these two sets of data points are for highways. If we exclude these two bunches of data, we can say that these data points are well estimated in NC16, but we should say that for the highways, highways are underestimated in NC16. And here is the calibrated free flow speed and capacity classified by the number of lanes. On the right hand side we have the capacity, on the left hand side we have the free flow speed. They have the same pattern. I would like to show you two interesting things on this diagram. First, as you can see, there is a large variation in free flow speed and capacity for the road segments that have 3 lanes. And also we can see that for the road segment that only have 1 lane, the mean value is much higher than the value that we have for the 2 lanes. This might, we can say that this is based on the fact that some of the road segments are located in the rural area, and these road segments are two-way roads that have 1 lane per direction. And on those road segments, we have higher speed limits, and based on this fact, we will see higher capacity and free flow speed through that 1 lane road segment. Here is the results of the third stage of the clustering. As I said, I applied 3 stages of unsupervised machine learning method. In unsupervised machine learning method, we don't have labeled data. Here, I have labeled the clusters based on my own intuition. I choose the number of clusters to be 4, and I named it as urban, suburban, rural, and freeway. Here we have the diagram. As you can see, this diagram is based on the calibrated data. As you can see, the machine learning framework that I have proposed have detected the freeways in an accurate way, and also it has detected the urban road segment in a well order. Most of the urban cluster are located in downtown core, and the pink and red road segments are located in the borders of this region. Afterwards, I saw the land use distribution among each cluster. For the urban, we saw that the residential land use is dominant compared to other land use category. And for the rural, we can see that open area have the great proportion of the land use category within the road segments in this cluster. We can say that we have mixed land use through the freeway and suburban area. And also we examined the number of lane distribution among each cluster. For the urban and suburban region, suburban cluster, we can say that most of them have 1 lane or 2 lanes road segments. But when we get to the rural and freeways, you can see that there are road segments that have higher number of lanes. For the rural, it is interesting to see that for the rural road section, we have 1 lane road segment. As I said before, this is for the 2-way roads that are located out of town, and they have higher speed limits and they can accommodate for traffic. And here is the posted speed distribution among the clusters. We have the same pattern for the urban and suburban region. As you can see, most of the road segments have 50 to 60 kilometers per hour free flow speed. When we go to the rural and freeway cluster, we can see that most of the rural clusters have 70 to 80 free flow speed, and most of the road segments that have highest travel speed are located in the freeways. This is the conclusion of my thesis. First and foremost, we talk about the free flow speed and we compare that with the NCS16. The existing free flow speed in NCS16 is overestimated compared to the real world calibrated data. And for the capacity, if we exclude the highways, we can say that the road segments in the NCS16 is well estimated in regards to the capacity. But for the highways, we should say that NCS16 underestimated this value. And also, we looked at the speed limit, number of lanes, land use adjacent to the roadway, and we see the influence of these attributes on the performance of the roadway. We have some limitations for our study. The generated metrics that we use from street lights data was not precise enough in order to model the traffic behavior. We faced some problems in regard to the abnormal traffic value, and maybe in the future they can generate some accurate results, because the data that they are processing is just based on some probe vehicles in the roadway, and they use some machine learning method to generate the transportation metrics. It's really innovative to have such a data platform, but it needs more works in order to get it better and better. Right now, I have calibrated the road functional classes for the static traffic assignment. And but this static traffic assignment cannot portray the dynamic nature of the congestion. We have to step forward to the dynamic traffic models. Right now, some groups at University of Toronto are developing dynamic traffic assignment in AMSON, which were under construction when I was doing my master thesis. There are some future works that others can do. First, the framework that I have proposed can be used with other data sources. For example, one can use loop detector data combined with Google Map API and generate the metrics. The framework that I have proposed is not region specific, and it can be transferred to other places in the world. Also, one can consider the impact of truck, weather, and capacity drop on the performance of the roadway. I didn't have labeled data for the truck and also capacity drop, but one can find this data and label the data and do some metrics from that. And the last future work that can be done is using the historical route choice model for calibrating the congested part of the video function. And here are the references of my study. Thank you for hearing my presentation, and I'm here if you have any questions.